In this unit 5, we look at functions of 2 variables and 3 variables. You're all familiar with functions of 1 variable. Function of 1 variable, we usually visualize like this. We look at the graph of the function. So here in this case, if I would take the function f of x equal to x squared minus 1, then this figure which I have here is just a figure y is equal to f of x. And that's what we call the graph. And now, today we deal with functions of 2 variables and functions of 3 variables. Let me just tell you how you graph this. So if you have a function of 2 variables, like this, we can also draw the graph. Now this is in 3 dimensions. So we have x, y, and z. And now what this means is we draw here for every x and y, we draw the z value. So this means, for example, for x equal to 0 and y equal to 0, then when we are here, we take the value minus 1. If x is equal to 1 and y is equal to 0, we get the value 1. So we have a then we get the value 0. So that's here. And also when y is equal to 1 and x is equal to 0, we get the value 0. So what we can do is for every x and y, so we have given x and we have given y, we can draw our function value fxy as the height. And then we do that at every point, we get a graph. Let me just draw this. You can actually see what happens here when y is equal to 0. You should get a parabola. So this is this parabola here. This is actually when y is equal to 0. So let me just actually draw this here. And right now here this is a z, and then what we have is we have this we have a parabola here. And also when x is equal to 0, we see a parabola. So we see actually this is a parabolic shape. And if we draw that, if you look at it, also just depends only on x squared plus y squared, which means it only depends on the distance to the origin. So what happens here is that we get a graph. It looks like that. And this is called the graph. Now in general this is difficult to draw, and we have a calculator, graphing calculator or Mathematica, which can do that very well. So that's one possibility how we can visualize the graph. Also, maybe here in this case, what was important were the roots. So these were the places where the function were 0. And also here we actually see the function is 0. When the function is 0, when z is equal to 0, we see x squared plus y squared is equal to 1. So we see actually these are the roots. They're also called traces because it's an intersection with the xy plane. And then we have seen the other traces here. These were parabolas. We will come to that in a second. So there is another way besides just visualizing the function using the graph, is using a contour map. So what we can do, that's a little bit easier to draw because we are in 2 dimensions. What we can do is we can draw for every z value, we can draw the contour. So for example, we can draw x squared plus y squared is equal to minus 1 is equal to 0. So that's the root, right? This is the place where the function is equal to 0. and these are the roots. And we have already seen it here. So that's a circle. X squared plus y squared is equal to 1. So in this case, that would be a circle. That's when z is equal to 0. Now, let's look at another value. So that was this root here. We can also see, for example, what happens when x squared plus y squared minus 1. The function value is equal to 1. So then we see x squared plus y squared is equal to 2. So that's a little bit the bigger value. So we get this. This is a radius square root of 2. And what happens when x squared plus y squared minus 1 is equal to minus 1? That's an interesting case, right? When x squared plus y squared is equal to 0, then we are here. So sometimes these contours are just points, or they can also be empty, right? When we take minus 2, we get something minus 2, we get something equal to minus 2, we get something empty. So these are called contours. Or level curves. That's the same word. Contour or level curve. And if we draw all these level curves, see they're all circles. So what we get, the contour map. So these are the two ways how we can visualize the function. This function here was visualized as a graph, as a three-dimensional surface, so a surface in 3 dimensions, or just a bunch of curves in 2D. And you're all familiar with this, right? If f is equal to is a height, that's kind of what we have here. And these are the contours. These are isoheights. If fxy is the temperature, you see that often temperature maps, right? So the temperature, these are isotherms. When fxy is a pressure, then the contours are isobars. So that's just a little bit of terminology which shows that this appears often in applications, like in maps, weather maps, or maps which tell you how high you are at a specific point. So in this case, we are at the lowest here, and we are going up when we go away from the origin. Okay, let's start with something which we have seen already almost. So let's take fxy is equal to 4 minus x squared minus y squared. So what I have here, I take the function, then I draw here the graph. So let me just make a little table. It's the simplest. So we have the graph, and then we have the contour map. So in this case, it's very similar to what we had before, but just now the sign has changed. So what happens here in this case, the graph was before a parabola like that, kind of paraboloid like that. Now it's upside down. So let's just draw that. You can see where it the intercept with the z-axis is when x and y is equal to 0. That's the value here. So it is at 4. Right, and then it goes down when x and y, when z is equal to 0, then this means x squared plus y squared is equal to 4, which means a circle of radius 2. So that's the roots, right? Circle of radius 2, and then the graph looks like that. It's also paraboloid, and also here, if this is equal to constant, we still get our circles x and y. Now I take a second example. In class we will look at much more examples, but a very important example is if you take fxy is equal to x squared minus y squared. So in this case, this is not, you see we have one minus sign here. Maybe it's easier to draw first the contour map. So what happens if this is equal to 0? What happens if this is equal to 0? That's the root. So if you have x squared plus minus y squared is equal to 0. If you look at that, that means actually x is equal to 0 or x is equal to minus, x is equal to y or x is equal to minus y. So this is the root. And you might be, especially after having worked on the homework for today, you might have seen that x squared minus y squared is equal to 1 are hyperbolas. And let's also look at the case x squared plus minus y squared is equal to minus 1. You can kind of see, you know, if you put y is equal to 0, you see it intercepts here at 1 and also here at 1. But what happens is if you look at all these contours, these are all hyperbolas. So these are hyperbolas. So this is a very important example, and you have it always on your hand. When you make a fist, you see this saddle type situation. So we are going up here, and then we are going down here. So one way to draw this is maybe one way to draw this is like that. So that's the surface. It's a hyperbolic paraboloid. This is a paraboloid. Actually elliptic paraboloid. This is a hyperbolic paraboloid, and in this case the roots here are here. So you can actually see that here. I'm drawing these roots here on my result when I would cut it at this height. So all these contours are what you get when you cut it in different heights. When you cut this surface in different heights, you get these curves. Maybe another example, and then I'm moving on. If we look at class at more examples, let's take an fxy is equal to 6 minus 2x minus 3y. And you are all familiar with this already from last time. Right? When we write this equal to z, and when you write this equal to z, then you see that 6 z is equal to 6 minus 2x plus 3y. So that's a surface we have seen last time. It's a plane. And so what we can look at is what happens when z is equal to 0. So when z is equal to 0, we see z is equal to 0 gives 2x minus 3 plus 3y is equal to 6. That's this root. In this case, then x is equal to 3, y is equal to 2. So this is a line. We can also look where it intercepts the z-axis. When x is equal to 0 and y is equal to 0, we see that this is actually hitting it here at z is equal to 6. And so the surface which we get is this plane. So it's an infinite plane. So this is a plane. It is of the form ax plus by plus zz is equal to d, right? When we write it as fxy is equal to z, that's of this form. And we can also draw the contours here. So contours already, one contour we have already seen here, and x is equal to 3, and this is equal to 2. This is one contour, and all these other contours are parallel. So when you take this this plane, take this plane and you cut it at different heights, you get always lines. So that's the lines which we see here. When we look at functions of 3 variables, we can no more draw the graph. Let's take an example. So this could be a temperature in space, telling you at x, y, z what the temperature is. But we cannot draw the graph, right? Because we would have to draw it in 4 dimensions. We would have to say maybe w is x squared plus y squared plus c squared, but we don't have a 4-dimensional space to draw in. So the only thing we can do is we can just look still at the contour, at the level surfaces or contour surface. So contour surface. So what we can do is we can look at fx, y, z is equal to constant. We can draw several of them, or we can just draw one of them. So in this case, what happens in this case is that in space, when z is equal to, and c is equal to 0, and then we don't get any surface, we are here, but when c is equal to 1, so c is equal to 0 gives us just a point, but c is equal to 1 gives us something interesting. The surface we have seen last week, right? So this is a sphere. So these are spheres. Could also be a point, or it could be empty. For example, fx, y, z is equal to -1 doesn't give us anything. So we can draw all these contours. Usually we just draw one of them, and this is a function of, this is how we visualize a function of 3 variables. But they're very beautiful, and I show you a couple of level surfaces then with a computer. For now, we will focus on some quadratic surfaces, but let me just actually tell you two more examples. So what happens if you take fx, y, z, 2x plus 3y plus c's, and we take this equal to constant. What do we get? So in this case, the function fx, y, z was linear, and what we get are nice planes, right? So we have a 3, 2, 6. So this is one plane. So then when this is equal to 6, for example, this is f is equal to 6. When f is equal to maybe 12, it is something like that. And so on. When f is equal to 0, we have a plane which goes through. So all these planes are infinite planes which foliate the entire space. So these are the contour surfaces. So that was the sphere case, important case. This is the case of a plane. Let me also take the example which we have just done last time. Let's just take fx, y, z is equal to z minus maybe x squared plus y. So in general, we can take z minus gxy, where gxy is a function of 2 variables. So in this case, if this is equal to 0, we have already, or equal to -1, we have already seen what the level surfaces are. Right? In this case, the level surface we have already seen as a parabola, which is kind of below. So this when z is equal to when c is equal to -1. When c is equal to 0, then we have a paraboloid which is going up a little bit. See kind of different paraboloids. Okay, we look at quadrics, something which the Greeks already were very fond of. And let's just do it in the order like here already listed. So there are 3 major types: the ellipsoids, the paraboloids and the hyperboloids. And then there are the specials, and they're actually the most interesting ones. We will see them a lot. And so let's start with the ellipsoids. So that's part A. So you're all familiar with a sphere, right? X squared plus y squared plus c squared is equal to 1. So that's a sphere. It's also called the unit sphere. Now what we can do is we can deform this sphere. We can, for example, say x squared over 4 plus y squared over 9 plus c squared over 36 is equal to 1. So what we get here is something which looks like a sphere, but it's deformed. So what happens is, if you want to see how this looks like, we actually can do that. We can see, okay, what happens when y and z are equal to 0. So what we actually do is we compute the intercepts, the intersections with the axis, with the coordinate axis. These are called intercepts. Very important. And then we have also the traces, intersection with coordinate planes. So these are two very important things. In this case, the traces were just circles here, right, going around. In this case, what we can do is, if you look at the intercepts, x is equal to 2, right? That is one, and x is equal to minus 2 is another one. Y is equal to, when we take x and z is equal to 0, we see y is equal to 3, and y is equal to minus 3. And then when x and y are equal to 0, we see that z is equal to 6, so minus 6. So what we get like that, we can see how this sphere has been deformed, and so what we get is we get what we call an ellipsoid. So that's all. We just deform it like that with usually I write a square, b square, and c square here, so that we can see the intercepts here. And if you look at the traces, for example, if z is equal to 0, we get the roots. So this is the trace. This is x squared over 4 plus y squared over 9 is equal to 1. That's an ellipse in the xy plane. So we can like this. Also, the other traces are ellipses. So if all the traces are ellipses, then we have an ellipsoid. And we can also move it around. For example, x minus 3 squared over 4 plus y minus 16 over 9 squared over 9 plus z minus 1 plus 1 squared over 9 over 36 is equal to 1. So in this case, everything has just moved over. So this is translated to, so that this ellipsoid has been just translated to the center. And the center is then just 3, 16, and minus 1. So this is at the center and afterwards of the ellipsoid. So similar how we have done that with spheres. We can just move them around. You can also use completion of the square to find this form. In this form we see really what is going on. Okay, paraboloids come in two shapes. They're elliptical paraboloids and hyperbolic paraboloids. So let me just put that here. So these are the elliptic paraboloids. We have seen both. And then we have the hyperbolic paraboloid. So these are all graphs of functions. So we have, in this case, we have z is equal to x squared plus y squared. That's kind of simplest form. And then the hyperbolic paraboloid, which is z is equal to x squared minus y squared. In this case, one way to draw that is actually it's hard to draw this hyperbolic paraboloid, but this is a saddle. So this is also a saddle. And we have seen already here, in this case, there's these traces, right? When you intersect the paraboloid, this hyperbolic paraboloid with z is equal to 0, you get this cross. And you can also draw the traces. Z is equal to x squared. That's this trace here. That's a parabola. It's x. And then the other one is here. So this goes down. There is another trace. Z is equal to minus y squared. That's the trace when x is equal to 0. So there is one way which goes down like that, and one way which goes up like this. So there are three different traces here. Lines, parabola down, parabola up. And also here we can just deform this, and we can say x squared over a squared, y squared over b squared. Then we have ellipses here, x squared over a squared, y squared over b squared. We can just make that, deform that. So this is actually inside here. So that's a parabola. So that's a parabola. You see that parabola here? And inside is this asteroid, piece of asteroid. I've placed this inside here. And then there's this illusion which makes it appear coming out. That's pretty cool, without any hologram techniques or anything. It's just optics. So how do we draw this? So what we can do is we can look at the traces. So the traces are really important, and also the intercepts. But what happens when this is equal to z is equal to 0? That's an important one. And we see a circle. And z is equal to 0, we get x squared plus y squared is equal to 1. Now, if you make z bigger, for example, if z is equal to 1, then you take it on the other side, it becomes bigger, the circle becomes bigger. So when you look at z is equal to 1, the circle has become bigger. And also when z is equal to -1, the circle has become bigger. Now it helps also to look at the traces. So if y is equal to 0, then we are in this plane here. When y is equal to 0, we get x squared minus c squared is equal to 1, which is a hyperbola. So we see that this is actually a hyperbola also. So what we see is this one-sheeted hyperboloid looks a little bit like this. Now, there's a change here when you take a x squared plus y squared minus c squared is equal to -1, because if you put z equal to 0, you see there is no intersection here. There's no root, no xy trace. This means when we take the xy plane and intersect it with the surface, we don't get any intersection. It means this surface is divided in two parts. And if you look at the intercepts, you still, if you look at the traces, you still see when x is equal to 0 or y is equal to 0, they are still hyperbolas. But the hyperbolas are now like that. So what we have is, and then we get also when z is equal to, maybe z is equal to 2, we see x squared plus y squared is equal to 3. So we get circles. So this we get circles here as generalized traces when we intersect it with z different from between -1 and 1. So there is no intersection here. So we have two sheets. And also here we can just change that, deform that. And get, elliptical versions of it. Okay, before I forget, the hyperboloid, I should have said that before, has actually a very nice property. The hyperboloid you can get by taking a line and turn it around. So if you take a line and you turn it around, you get this surface. You can see this maybe with spaghetti. I'm not sure they are breaking very quickly, but when you take spaghetti and you turn it around, you actually see this, you see a hyperboloid appearing. And that's also why hyperboloids appear in construction, right? Because you can actually put sort of cooling towers, for example. F, X, Y, Z is equal to x squared plus y squared minus c squared. And let's look at these level surfaces here. So we have already seen that in the hyperboloid case. So in the hyperboloid case, when we get this, for example, we get this one-sheeted, actually one sees it not badly here, this is this one-sheeted hyperboloid. So if you see this one-sheeted hyperboloid, so x squared plus y squared minus c squared is equal to 1. So what we had is we have this one-sheeted hyperboloid. Now, if x squared plus y squared minus c squared is equal to minus 1, we have seen this is also a hyperboloid, but a two-sheeted hyperboloid. Now you might wonder what happens when x squared plus y squared minus c squared is equal to 0. So that's just between that. We have three cases here. Kind of like a movie, we can deform it from here to here or from here to here. What happens in this case when x squared plus y squared minus c squared is equal to 0? You can actually see that x squared plus y squared is equal to z squared then. And you can look at the traces, like when z is equal to 0, you just have a point. When z is when this is equal to, when z is equal to 0, that's just a point. But when z is equal to 1, you get a circle. And z is equal to minus 1, you get also a circle. And these circles become smaller if you get closer to the origin. So what this actually is, this is a very important shape. It's called a cone. So this is kind of just the case when this hyperboloid goes over, becomes this hyperboloid. So it's kind of a singular case. It has a singularity here. So that's one of the important special. Okay, if you look at the cylinder and say this is equal to constant, we have already seen what happens. When this c is equal to 1, so c is equal to 1, we have seen there's a cylinder which has radius 1. When c is equal to 1/2, and it's just a smaller cylinder, like this. These are cylinders, pipes. And so when c is equal to 2, then the cylinder has, the radius has grown. C is equal to 0 is an interesting case, kind of a limiting case when we have actually just a z-axis. So that's these are also very important surfaces. Now again, in order to see that, we can see that when we take z is equal to constant, we see always the same trace, right? They are always the same circle. Doesn't matter which height you take. Doesn't matter what z you take. And this is in general when you have a surface like this, where only two variables appear, then this is cylindrical. It's a cylindrical type surface. So if you look at this case here, x squared minus y squared, and you take this equal to constant, like 1, you see here there's a hyperbola here. But now also it doesn't depend on z. Right? That's why you have this shape. So that always happens if you have a surface which doesn't depend, if you have a function which doesn't depend on z. So what happens is this produces a cylindrical type also here.